Welcome everyone. My name is Steffen Hädrich. I'm with Active Fiber Systems, a fiber laser company based in Jena, Germany. And today I would like to present our recent results on a high average power CEP-stable fuse cycle laser system that we are building for ELI-ALPS Research Institute in Szeged, Hungary. As you can see, there's already quite a few number of people that are involved into this project, namely from Active Fiber Systems in Jena, but also the University of Jena and Fraunhofer Institute in Jena, as well as different institutions across Germany, and of course the ELI-ALPS research facility itself. Active Fiber Systems is a rapidly growing company which has the mission to transfer research results into reliable, commercially available systems. Our main markets are in fundamental science, materials processing, and life science, and today we are the technological leader for high-power ultrafast fiber laser systems. We recently moved into our new building, which has more than 1,000 square meters each of lab space and office space. Our products range from oscillator types or car sources to 100-watt glass laser systems, going into the multi-millijoule kilowatt level with coherently combined laser systems. And we recently also launched the 2-micron line, which is catching up in performance with the 1-micron systems already. So we can add fuse cycle pulse compression and CEP stability to the systems. That's something I would like to talk about in more detail today. We can also offer coherent XUV sources based on high harmonic generation. We can generate mid-IR radiation. We can customize pulse patterns, and we can further extend the range of our systems by using OPAs. So as I said, today I would like to focus on the HR laser systems, which are the high repetition rate laser systems of the ELI-ALPS research facility. These are actually 2 systems and 2 of the 6 main laser systems used in the facility, which are used to drive attosecond beamline. The HR1 system is already delivered, which has parameters of 1 millijoule and 100 kilohertz repetition rate, equaling 100-watt fuse cycle laser system, and it will be upgraded in terms of CP soon. The HR2 system will be installed early 2021, and the main difference between HR2 and HR1 are the pulse energy, which is 5 times higher for the HR2 system, meaning that the average power also is as high as 500 watt for this fuse cycle laser system. So here's a schematic layout of the HR2 system. It starts with a CEP-stable oscillator, which is followed by a preamplifier chain, which includes the pulse stretching, pulse picking, and phase, and also amplitude shaping of the pulses. And the main part here is a 16-channel coherently combined main amplifier system, which is used to boost the output of the preamplifiers. And finally, the pulses are compressed in a CPA compressor and then sent into a spectral broadening and pulse compression stage, which is used to achieve the final output parameters of the system. So here's a look into the laboratory, actually. So this is the 16-channel main amplifier box of the HR2 CPA system. It has 8 channels on the lower level and 8 channels on the upper level. And these 16 channels are then combined to achieve the output power performance of the system, which is more than 10 millijoule of pulse energy at 100 kilohertz repetition rate. So that means the average power is higher than 1 kilowatt, and the compressed pulse duration is less than 300 femtosecond. So on the left side, there's a graph of a long-term measurement of the output of this system. Here we measure the average power over more than 9 hours. And as you can see, we achieve an excellent stability of about 0.3% over this 9 hour of measurement. At the same time, we have an excellent beam pointing stability of about 6 microradian and 12 microradians in X and Y direction, respectively, also measured over this 9 hours. And the measured pulse quality with M square 1.1 is also very excellent. To compress the pulses in time, we utilize a technique of stretched hollow core fibers, which has been pioneered by the Laser Laboratorium Göttingen by Tamas Nagy and Peter Szymon. On this topic, we also cooperate with the Max Born Institute in Berlin, since Tamas moved there. And the benefit of this technique is that the fibers are pulled. By that, they are very straight, and bending losses are essentially eliminated, which means that we have the lowest possible propagation losses in the capillaries, and therefore these are very well suited to high average power laser systems. In our case, we use fibers of 6 to 8 meter length with an inner diameter of 400 micron. And currently we fill the fibers with argon gas with a pressure gradient of 800 millibar at the input facet and about 1.9 bar at the output of the fiber. So here's a more detailed view of the pulse compression unit. So the CPA is the same as we have seen before. We have an in-coupling chamber into the hollow core fiber, which can be up to 8 meters of length, an out-coupling chamber, and then finally a compressor chamber, which houses the chirp mirror compressor that is used to compress the pulses in time. So in the first set of experiments, we used a bit more than half of the performance of the system. So we had close to 600 watt, 6 millijoule femtosecond pulses from our CPA system, which we were launching into a 6 meter long hollow core fiber. And here on the right side, you can see the output power in blue with respect to input power, and in orange, the transmission also with respect to input power. And as you see, if we ramp up the input and output power, the transmission more or less stays constant over the whole range of operation. And at the maximum available input power, we achieve more than 300 watt of output power in the end. And as you can see here, we also maintain a very good beam profile, which here is measured at this maximum output power of 320 watt after the fiber. So we compress the pulses in time and measure the compressed pulse duration with a D-scan measurement shown here. And actually, with this measurement shows that we are just below 10 femtosecond in pulse duration, validated by this D-scan measurement. So that means we have demonstrated 320 watt of average power at 100 kilohertz repetition rate and the pulse duration of around 3 cycles. So of course, one of the most important parameters of the systems is the CEP stability. So we would like to have a closer look on that. So as I said in the beginning, we start with a CEO-stable oscillator, which is measured here. So the important curves are the orange ones, which show the power spectral density, solid curves, and the integrated phase noise, the dashed dotted curves here. And our oscillator has a bit more than 100 milliradians of integrated phase noise when we integrate for frequencies from 10 Hertz to 20 megahertz. In the system, we implement a CP preserving pulse picking, which we have shown in an earlier publication. And of course, we also have put a lot of effort in the most stable system design that we can achieve to also help the CP stability. Of course, there are some questions that come to our mind when building up the system. For example, how does the large stretching and compression affect the CP stability? In particular, what does the big grading compressor introduce in terms of CP noise into the system? And of course, another important question is, how does the coherent combination process affect the CP stability? So to get a bit of a better picture on that, we started with a set of experiments which were focusing on investigating some general properties of the CP or CEO stability. And for that reason, the system has been running at full repetition rate of the oscillator, which is 80 megahertz. We can operate the system from 1 to 16 channels, which means that at 16 channels, we have about 1.1 kilowatt of average power available. So the output of our system is then attenuated, the CPA system is attenuated, then sent into this nonlinear pulse compression stage, which pre-compresses the pulses in time, which are then used to generate the necessary supercontinuum for 2 F2F interferometers. So the first one is used as an in-loop interferometer to generate the necessary error signal, which is then fed back onto a EOM in the system to stabilize the CEO. And the second F2F is used to measure the CEO stability out of loop. So as I said, by that we can study some general noise properties of the system and also the coherent combination process itself. So this is a first measurement of one channel operation of the system. So on the left side, you will always see the CEO noise power spectral density, and on the right side, the corresponding integrated CEO noise. So all integration has been done from 10 Hertz to 20 megahertz. And in this free running configuration, which means that only the oscillator is stabilized, we achieve about 700 milliradians of CEO noise. But what's important to note is that this noise, as shown here and here, is mostly located below 1 kilohertz, which means that it's suitable for a feedback loop. And we have just done that. When we apply this feedback loop, we can obviously suppress most, if not all, of the acoustic noise. which shows up in the power spectral density, but also in the integrated phase noise, which drops to 220 milliradians in this case. We validated this by measuring out of loop. So again, we have very similar results, which means that we can trust these measurements. So of course, the more important question is, how does this evolve with a varying number of channels? So we repeated these measurements. So again, we started with 1 channel, so that's the measurement I have shown before. Then we increased the number of channels to 2, to 4, to 8, and finally to 16. And as you can see, except for some fine details, there's virtually no difference between all those measurements, meaning that also at full average power of 1 kilowatt, more than 1 kilowatt, we stay at this 220 milliradians of CEO noise. And this is very important because this means that the coherent combination does not affect the CEP noise of this system. So of course, the more important question is what happens at the final output of the system, then at 100 kilohertz repetition rate. And for that, we measured at this output with a stereo ATI phase meter. In this case, we used a commercial device from Single Cycle Instruments. It's a company also in Jena, Germany. And this ATI phase meter has the capability to measure each and every shot of our 100 kilohertz pulse brain. So these are measurements that have been done at the system output. The left graph again shows the CEP noise power spectral density, and the right graph the integrated phase noise. And in this first measurement, we end up with about 1 radians of integrated noise. But what's important to note is that most of the noise is actually located at high frequencies above 1 kilohertz, which means that the CEP is dominated by white noise. So we went into some of the details of the system, and finally were able to identify one particular issue. And this is mostly dealing with electronic noise sources. And when we kind of improve this parameter, then we are able to significantly reduce the white noise, which is shown here in the power spectral density. And at the same time, also the integrated phase noise drops to already below 800 milliradians. And we did a first feedback test here, and similar to the results for the CPA itself, we are able to suppress this low frequency part and ending up with less than 580 milliradians of, or about 580 milliradians of integrated phase noise in this intermediate system status. So we are further improving this very important parameters, and we're actually confident that we are converging towards sub 300 milliradians. So we have identified a few other things. And we're also able to demonstrate this value previously in another system. So in summary, I've shown that we already have a long-term stable 10 millijoule, 1 kilowatt, 300 femtosecond fiber CPA system, which can be used for spectral broadening. So in the first step, we were able to achieve multi-millijoule free cycle pulses at 100 kilohertz, which is already an average power of 320 watt. We have shown that CEO stability of 16-channel coherently combined fiber laser system with more than 1 kilowatt of average power can be demonstrated, showing a very good value of 220 milliradians. And we are currently working on the CEP stability of the final system output. And we are standing at 580 milliradians at the moment, but we are converging towards sub 300 milliradians and expect this value to be measured very soon. And with that, I would like to thank you very much for your attention.